Gravitational waves were hypothesized in 1916 by Albert Einstein as a consequence of the general theory of relativity. Part of what general relativity states is that large, massive objects like planets, stars, and black holes create gravity wells in space-time. And when two very massive objects collide, such as when a black hole merges with another black hole or a neutron star, disruptions are produced that echo through the universe. Ground-based observatories like LIGO were built to detect these large, violent waves as they pass through our planet. But there's a second effect. In the 1950s, when the cosmic microwave background was first discovered, it was proposed that gravitational waves could create a similar background. And in 1982, a couple of researchers developed a theoretical and mathematical framework for detecting these waves, and they proposed using pulsars to do it. In a recent study, researchers used 15 years of pulsar data to analyze the gravitational wave background and to see what it can tell us about supermassive black holes, specifically how they orbit around each other and eventually collide. I want to talk about millisecond pulsars, gravitational waves in ground-based observatories, how pulsar arrays work, and what the researchers concluded. I'm also going to talk about another study that looked at non-standard cosmological models from the new physics, which includes inflationary gravity waves and cosmic superstrings, and what this data means for them. So let's get into it. I'm Cameron, and this is my channel. Welcome to the Sexy Universe. The data this study is based on comes from observing 68 millisecond pulsars. Here's a quick overview of what they are. When a star between 10 and 25 times the mass of our sun begins to run out of hydrogen in its core, it switches over to fusing heavier atoms. While the energy output per atom is smaller, a much larger number of them are fusing at any given time. So the overall energy output greatly increases. This pushes the outermost layers of gas even further from the core. And this is the beginning of the star's red giant phase, which actually consists of many cycles of collapse and reignition. During the course of this phase, heavier and heavier elements undergo fusion, but each step up in atomic number yields less energy. The theoretical endpoint of all this is iron, because the energy input to generate fusion in iron is less than the energy output. But in most stars, fusion stops way before this point is reached. When fusion stops entirely, all the star's gas and dust collapse toward the core. All this material hits the core at incredibly high speeds, and this generates massive pressures and temperatures. The temperature and pressure are enough to force the electrons in the atoms at the core of the star into the atomic nuclei where they merge with protons. When this happens, the proton and electron pairs convert into neutrons, releasing a whole lot of neutrinos and a whole ton of energy. That energy is enough to blow all the remaining gas and dust clear from the core of the star. This is called a supernova, and the product of a supernova like this is a neutron star and a nebula. The first supernova ever observed in human history happened in 1054, and it produced the Crab Nebula, which has a neutron star in the middle of it. Astronomers at the time obviously didn't know this was a supernova. They called it a temporary star. The gas in the Crab Nebula is still expanding away from its neutron star at a rate of about 1,500 kilometers per second, or about 0.5% of the speed of light. Theoretically, neutron stars can be anywhere from 1.4 solar masses to 3 solar masses, but the vast majority that have been observed are between 1.4 and 1.5 solar masses, so at the lower end of that spectrum. The heaviest neutron star that's been observed is 2.35 solar masses. The diameter of a neutron star is somewhere between 12 and 20 miles. Since neutron stars are both heavy and compact, they pull in a lot of material from around them. And that material gets to a very high speed as it spins down toward the surface of the neutron star. If a large object like a rogue planet or a regular star gets pulled in, the material making up that object can easily be scattered into an accretion disk. The accretion disk around a neutron star is very similar to an accretion disk around a black hole. And as material spins in around the equator, a lot of that material and radiation is emitted as jets from the poles. And the jets become observable whenever they're pointed toward our solar system. Since material falling into the star adds energy, it increases the neutron star's angular momentum, which in turn speeds up its spin. And this is how a neutron star becomes a pulsar. When a pulsar accretes enough material, its spin can get fast enough that it turns hundreds of times on its axis per second. At this point, it's called a millisecond pulsar because its frequency is in milliseconds. And the whole process of accreting material, speeding up its spin, and then slowing down can take tens of millions of years. And as a result, these pulsars give out very consistent, predictable signals. The general theory of relativity tells us that every object with mass produces a gravity well in space-time. The gravity well is at its deepest at the object's center of gravity, and it dissipates with distance. The more massive an object is, whether we're talking about a planet, star, or black hole, the deeper its gravity well is and the further out it stretches. This is also true for larger structures like galaxies and galactic clusters. These folds in space-time spread through the universe at the speed of light, about 186,000 miles per second. So powerful disruptions produce effects that spread across the universe like waves in the ocean. The difference is that at distances of thousands of light years, the measurable effect of these ripples is very small. In fact, detectors like LIGO, the Laser Interferometry Gravitational Wave Observatory, need to measure disruptions on the scale of 10 to the negative 21 meters. That's a billionth of a trillionth of a meter, a size so small we can't even comprehend it. And since these waves are traveling at the speed of light, they need to be detected very quickly as well. The LIGO detectors in Washington State and Louisiana have tubes that run 3 kilometers in length, which means a gravitational wave passes through them in a 10,000th of a second. Once a gravity wave passes completely through an object, any distortion to space-time is spread uniformly across the object, so the gravitational waves can only be detected as they're passing through. The detectors work by running a very powerful kilojoule laser and using a partially reflective mirror to split the beam. Part of the beam is split off at 90 degrees and the other part goes straight ahead. At the end of each of the tubes is another set of mirrors that bounces the beam back and forth several times before sending it back down its respective tube. At the end of the journey, some of each beam is sent to a detector that picks up the level of interference. Photons travel as waves until they're absorbed. So 2 photons with the same wavelength, which would be light with identical colors, can interfere with each other by either canceling each other out or by doubling their brightness. There are also gradations of interference between these two extremes. The LIGO detectors work by detecting and analyzing these different types of interference. I borrowed these clips from Craig Callahan, who created an excellent video detailing LIGO's interferometry. I'll put a link to his video in the description so you can watch it if you're interested in this incredibly interesting application of laser technology. The LIGO detectors are similar to regular telescopes in the sense that they look at large major disruptions that are immediately visible, but they're not capable of seeing the gravitational wave background. Just like a regular telescope can't see the cosmic microwave background. The cosmic microwave background was found in the 1950s, and it was pretty much speculated right away that there would be a gravitational wave background as well. The first pulsar was observed in 1974, and it wasn't very long after that researchers began to speculate that networks of pulsars could be used to look for the gravitational wave background. In 1982, Hillings and Downs published their work, which laid out a theoretical and mathematical framework for using millisecond pulsars to look for the gravitational wave background. And specifically, they proposed that it would look something like this theoretical curve. And since millisecond pulsars have stable frequencies over millions of years, radio telescopes can be used over time to monitor their changes and movements. Several projects have been established and they've accumulated data over the last 2 decades. These include the Chinese, Indian, and European pulsar timing arrays, the Parkes Pulsar Array in Australia, and NANOGrav in North America. Each of these projects collect data from between 15 and 68 pulsars, and these groups use radio telescopes to carry out their missions, such as the 500-meter spherical telescope in Guizhou, China. NANOGrav, which provided the data for this study, uses the Green Bank telescope, the Very Large Array in New Mexico, and CHIME in British Columbia to collect its data. There are several cosmological models that predict a gravitational wave background, and fortunately for us, they all provide modeling parameters. These theories include, among other things, inflationary gravity waves and cosmic superstrings. The cosmological model that's most accepted, Lambda-CDM, predicts that the gravitational wave background should mostly be influenced by supermassive black hole pairs orbiting tightly around each other. Black holes don't emit or reflect light, so there's no direct way to observe them. Instead, their presence is inferred by looking at the motions of visible stars and looking at how their paths are changed by large, unlit gravitational points. Of the black holes that have been located, the vast majority of them have masses below 150 solar masses. But an enormous amount of evidence has accumulated that at the center of every galaxy is a supermassive black hole weighing millions to several billion times the mass of our sun. A second thing we've noticed is that galactic mergers aren't just frequent in our universe, they are the norm. In fact, 53% of galaxies we've observed show evidence of mergers in their past. When galaxies collide and merge, it makes sense that their supermassive black holes would also eventually collide and merge. But this is where things get a little bit hairy. Every supermassive black hole in a galactic center has its own halo of gas, dust, and stars. And when the two start approaching each other, they also crash into each other's halos. This has the effect of spinning all the matter in those halos up. And as the supermassive black holes continually turn and arch toward each other, they keep on running into all this matter. Some of it gets absorbed, some of it gets thrown clear, but either way, it has the effect of slowing down the motion of these supermassive black holes. It's this slowing effect that allows the supermassive black holes to fall toward each other. But eventually, the material in the paths of these black holes is all either absorbed or thrown clear. And the two of them basically reach a friction-free equilibrium of rotation around a shared center of mass. And with nothing to absorb this orbital energy, they can stay in this dynamic for tens of billions of years. And theoretically, this dynamic is reached when they're within 1 parsec of each other. This is called the final parsec problem. That equilibrium, of course, can't go on forever because the second law of thermodynamics tells us everything has to fall apart, including black holes. And eventually, enough galactic material will make its way to this orbiting pair to cause that orbit to degrade. But as this graph shows, that can take tens of billions of years. And since our universe is only 15 billion years old, that means it may never have happened. Of course, as long as the two supermassive black holes are orbiting each other, they should continually crank out an enormous volume of high-frequency, low-amplitude gravitational waves. So that's the model the researchers used the data to evaluate. Does the data support a gravitational wave background that's primarily created by supermassive black hole pairs? The study was kind of a hybrid in this way. It used actual data to evaluate the consequences of a particular cosmological model. But the phenomenon in question, supermassive black hole pairs, isn't directly observable. So it's not exactly a modeling study, but it's not exactly an observational study either. And long story short, the researchers found abundant evidence that the gravitational wave background is created by supermassive black hole pairs trapped in orbits around each other. The significance level they calculated was greater than 99%, but I'll explain later why this isn't as conclusive as it might seem at first. Real quick, if you're enjoying the video and feel like you're getting something from it, now would be a good time to hit the like button and leave any thoughts you have in the comments section below because it helps the YouTube algorithm. I'm also hoping to get monetized someday, so if you'd like to hit the subscribe button, I'd greatly appreciate that as well. The data shows that not only are supermassive black holes abundant in our universe, they're heavily affected by environmental factors, such as gas and dust concentrations around them and stellar collisions. The bulk of these pairs that are noticeable in the background have a redshift of 0.4 or greater, which means they're 7 billion light years or further from our solar system. But even though most of the pairs are far away, the closer pairs have a bigger effect on the data. The strongest signals in the data came from supermassive black hole pairs, where the total mass of the pair is greater than 1 billion solar masses. And to give you an idea of the scale, the supermassive black hole at the center of the Milky Way, Sagittarius A, is only about 4 million solar masses. The supermassive black hole that's at the center of the Andromeda galaxy is estimated to be between 40 and 150 million solar masses. So pairs of 1 billion solar masses are enormous compared to what we've been able to locate in the nearby universe. The data also implies that most of these really enormous supermassive black hole pairs are within a redshift of 1, or less than 11 billion light years from us. Most of the data also corresponds to supermassive black hole pairs that would have separations between 0.03 and 3 light years, so 1 parsec or less. This supports the final parsec problem. But since the data also shows that environmental factors have a huge effect, it also implies that more material would be falling into these pairs than the models suggest. That implies that the amount of time it would take them to merge is much smaller than the estimate of tens of billions of years. The data in this study is isotropic, meaning that it has the same results no matter which direction you approach it from. And in a way, the pulsar array can be kind of thought of like a diamond, where each pulsar is another node in the crystal, but it's basically homogeneous all the way throughout. And the downside to this kind of data is that it's not a great differentiator between different cosmological models. As I mentioned earlier, the most widely accepted cosmological model is Lambda-CDM, where lambda refers to the dark energy constant and CDM refers to cold dark matter. And basically, it follows on the idea that galaxies and other large structures in our universe resulted first from pools of dark matter that later pulled in the reactive baryonic matter that we're able to see. But it's not the only cosmological model. This study examined alternative cosmologies and explanations from the new physics. They looked at things like inflationary gravitational waves, scalar-induced gravitational waves, cosmic superstrings, and phase transitions. To me, the most interesting of these is cosmic superstrings. And it might really be just because it has such a cool name. Cosmic strings are in turn compatible with string theory. I really like string theory because it's internally consistent. At the same time, I remain skeptical of it because its unique predictions haven't been experimentally verified. But the idea from string theory is that elementary particles are made up of very small vibrating strings that exist in many dimensions. And cosmic superstrings would be strings just like these that grew in size along with the initial inflation of the universe. So even though they'd only be as wide as a proton, they could extend hundreds of millions or even billions of light years. And their vibrations and interactions with other matter produce a gravitational wave background. The beautiful part about all this data is that it lets us examine and explore all these different ideas and cosmologies and lets our imaginations run and soar. But the same thing that makes it so beautiful also makes it very frustrating. I mentioned earlier that the data support the supermassive black hole hypothesis with greater than 99% significance. But it turns out a lot of these other cosmological models are also supported with the same degree of significance. So while all this is fun and interesting, it doesn't really rule out any of these other cosmological models. They're all still valid, helpful ways of thinking about our universe. The future, of course, is very bright because we're constantly getting better telescopes, better mathematical methods, better software and computers for analyzing the data. We're also discerning more and more pairs of supermassive black holes that are caught in their orbital dance, such as this pair in my favorite galaxy, UGC 4211. This pair should come within a parsec of each other in the next billion years or so, and hopefully you and I will be around to see it. And with a little luck, we'll also be around to see it many billions of years from now when the two of them collide. There are also plans to use pulsar arrays to pick up anisotropic data as well. And hopefully it'll be enough to disprove some of our competing cosmological models and refine the ones we have. And with a little luck, you and I will both be here to talk about it. I believe the ideal life is a non-stop dance of learning and growing. Thanks for learning and growing with me. I've put all the references for this video in the show notes, which are available at my website, thesexyuniverse.com, and I'll put links in the description to both of the research papers I discussed, as well as the show notes. And I want to hear what you think, so please put your thoughts in the comments section below. Don't forget to hit the like and subscribe buttons on the way out. Stay on your game, and I'll see you next time on The Sexy Universe.